All right, welcome everybody to week 6, day 2, part 2. So in the first part, we talked about the philosophy of functional programming and how functions, if you can, try and make them pure, which means kind of like algebraic. Yeah, I like the background too. Try and make functions algebraic, like an algebra, you take parameters in, manipulate them, pass the result back out. Now we're going to learn about non-pure functions. Yep. So we are going to learn today about void, and we're going to learn about call by reference, both of which sort of go against the functional programming philosophy. Okay. So here is a pure function that just takes in parameters and returns a result. Here is a void function. Void read xy. This is sometimes called a procedure or subroutine in the terminology of computer science. And so we can do something like this: int x equals read, int y equals read. If x is less than y, I don't know. We'll do nothing, but we'll pretend turn on the radiator. I don't know. Else if x double equals y, again, we'd have a function call here to something, turn off the radiator, and else do nothing but turn on the heat or something like that. So maybe x and y are like the current temperature and the ideal temperature, and so if the current temperature is over the ideal temperature, you expose a radiator to the wind and you cool the system down. If it's equal, I don't know, you retract it, just stay constant. And if the temperature is dipping, you turn the heater element on. And this code here would be like a control system for, like, I don't know, let's say you have a weather station out in, the middle of nowhere. And so it needs to regulate its own temperature. You might have this thing here run, every so often, right? And you could, of course, copy and paste this code, right? I can come in here and copy these things and paste them over and over again and just have right? You could, but then you would be violating the dry principle. Dry means don't repeat yourself. You guys need me to repeat that? No? Okay, good. Because I won't repeat myself. All right. So what I could do instead is, instead of copying and pasting those 5 lines of code over and over again, every time I wanted to, grab the temperature and extend or retract the radiator, I could just call this function here. So I could have some code, call it, and then 1,000 lines later I could call it again, and 1,000 lines later I could call it. You guys understand? And then if I had a bug in the code, like, I don't know, maybe I had a bug here or something, then all I need to do is fix it in one place. All of these things are side effects, right? Like I'm consuming data from the temperature sensor or whatever, and here we have a function call that doesn't exist. I just have a space here, but a function call to, like, extend the radiator fins to blow heat out. That's a side effect, right? Like, that is not a pure function. That is absolutely the opposite of a pure function. And what do we return from this function? Nothing. That is what void means. Okay, so learning point number 2 is we're doing the exact opposite of part 1, right? Learning point number 2, a void function can be considered a saved block of code that is rerun every time you call the function. Okay. So this is very different from, like, do you guys see the difference here? Like, this is like algebra, right? You've got inputs coming in, you manipulate them, multiply them, add them, whatever, and you pass the return value back out. With this guy here, these are like commands that we are just running. Okay, extend this, pull this data in, do this. I mean, they're both functions. Like, from C++'s perspective, these are just both functions. But, like, philosophically, a void function is different than this function, right? Philosophically speaking, like they're both like they both run the same way. Like you just go one line at a time, make a new variable, and do this, and make a new variable, and then move on. You know, like from C++'s perspective, there's no differences between these two things other than the fact that this does not return a value. Okay. Void functions return no value. Okay, you can return from them. So in fact, you can even do something like this. You can actually like do this and return. You can return that just quits out of the function. That just says fail, we're done, right? So if you had a cout statement down here, the cout statement wouldn't run if x and y were the same. It would just quit. It just quits from the function. It goes back into main and does its thing. Okay. So you can return from a function, a void function, but you don't return a value. There's no value. That's what this means. What is the return value from the function? There isn't one. So what would happen if I tried couting? What would happen if I tried couting the value, the return value of this function? So I'm going to call readxy, and whatever value it returns, I'm going to print to the screen. So what is this going to print to the screen? What do you guys think? Nothing. It prints the void. Stare not into the void, lest it stare back into you. What do you guys think? Will this even compile? Would it make an error? I'm not seeing one yet. Yeah, absolutely. As long as I'm in insert mode, it's not going to show you the compile error. So yeah, you cannot print a void to the screen because it's not like 0. You know, it's not like returning 0. There is no return value to print, and so it cannot compile code like this. And you guys will probably do this at some point in your career. You're going to try scouting the results of a void function. You just have to remember, cout means print to the screen. Print to the screen is very different than returning a value, right? When you return a value, it's as if, like, if I say integer, goo equals f of 10, the return value essentially replaces this call here. So it's as if I had written 50. The return value, when it returns 50, it essentially takes the place of the function, right? The function's gone now, and 50 is there. And in fact, if you have an optimizer turned on, the optimizer will probably do that. It probably will just set Google. Sounds like baby talk. Set Google. Sure. Sounds less babyish. It's going to literally just write this code for you. It'll probably just delete the function entirely. But yeah, that's what the return value means. The return value means that value takes the spot of wherever you call the function. Does that make sense? When you have a void function, you can't do that because a void function does not have a return value. If I put in read xy here, you can't do that because there is no value to set Google to. Void. Yeah. Cout is a function. Cout is a variable. It's a global variable of type IOStream that has an overloaded double left arrow operator on it. So the function is actually double left arrow. Cout is a variable. So this is like you called operator double left arrow passing no stream by reference name cout, and well, you can't put a void in here, but put in 5 here. It's like a function call like this is essentially what's being called. So the double left arrow is the function call, and this is parameter 1, and 5 is parameter 2. So yeah, and you up here you can't like return void, like that doesn't make any sense. That's not legal. So if you say you're going to return an integer, return an integer. If you say that you're a void function, you just return and destroy. If you try returning a value, then you get an error there saying it's a void function, don't return a value. We all do it every once in a while when we forget. We try return 0. It's not a big deal. Now the void function you guys might have seen already is called die. I use this in most of my homework assignments because it gives an error message that is predictable. A lot of computer science professors will have different error messages for all the different kinds of errors. Error, temperature too high. Error, temperature too low. I find it easier to just, when I'm writing test cases, just die, and then, if die, right, Reaper. And the reason why this is a void function is the exit function quits, right? The exit function actually kills your program. So if you call exit, that terminates your program. That's it. It's done. So do we have an opportunity to return a value? No. So die should be a void function, right? Because it's is this pure or impure? What do you think? Is die a pure function or an impure function? It is 100% impure. Like it is the most impure of all impure functions because it takes no parameters, returns no value. It has a side effect by couting bad input, and then it terminates the entire program. Like that is the biggest side effect you can have. It just dies, right? So this is definitely a impure function. A pure function is something that only operates on things within its scope, so to speak. Okay. So we call these void functions procedures or subroutines, and they're basically just like saving blocks of code that we could run repeatedly, so we don't have to repeat ourselves. Okay. All right. That's the first learning point for part 2 of the lecture. So we got up here, learning point number 2, and now we are moving on to the thing that causes students the most grief and trouble. The hardest to understand concept in C++, at least in C-Sci40, which is called call by reference. It's related to another topic students struggle with, which is called pointers. Okay? Very dry of me. Thank you. It's a very dry class. Maybe that's what they meant. Maybe they didn't mean to say this is a bland class. Maybe they meant to say this is a dry class. That's probably... He has a dry sense of humor because he repeats himself so much. Okay. So we're going to learn now call by reference, okay? Call by reference, like I said, students struggle with this. So prior to actually showing you what call by reference parameters look like in a function, I'm going to explain a little bit of background information about variables, okay? So if I have a variable here named int Bob is equal to 42, there are 4 things that I know about Bob. There's 4 things that C++ tracks. The first thing is the name of the variable. What is the name of the variable, everybody? What's the name? This is how the programmer refers to it, right? This is Bob, okay? What is the type of the variable? Which means how do the bits of the variable get interpreted? Or in other words, what kind of values can it hold, alternatively? It is an integer, right? So it holds whole numbers only from negative 2 billion and change to positive 2 billion and change. Okay. But what this really means, because remember, every variable, whether it's an int or a float or a char or whatever, is really just ones and zeros under the hood. And so if I were to set Bob to 101010, like this, I'm setting the bits directly on it. What value is this going to have if I see out Bob? Or is this a compiler error? Can I do this? Can I set an integer by literally just handing it a bit pattern and be like, this is you now. You are what was that? 26 zeros and 101010. Can I do that? Is that legal? Do you know what value Bob's going to have? Do you know binary? So in binary, let's do like 4-digit numbers. Let's make it simple. So in binary, we have 1, 0, 1, 0. In binary, the digits, we have the 1's digit, the 2's digit, the 4's digit, the 8's digit. Okay? And so if you have 1010 like this, that means the 8th digit is true and the 2's digit is true. So what value does Bob have? What is this going to print to the screen? Correct. 37, I'm getting a warning. Yeah, it's an empty, whatever. Good. No warnings now. Okay. But if this was, for example, a floating point number, this would be a very different value. What the type means is how do I interpret the bits within this variable? And there's all sorts of horrible ways you can actually get the bits of an integer into a floating point number. But here I'll just we'll do this. Printf. Printf. We're gonna print. It's gonna give me a warning. I know. I'm breaking it. Okay. I'm doing this intentionally badly. I know. Thank you for the warning. This is intentional. Thank you. 0. That's not right. That's not right. That's not right. And look, I'm trying to break something here. Stop trying to fix it for me. Annoying. All right, it is refusing to play ball with me. I triply floating point. Let me show you what it is in floating point numbers. So if we had 10, 10, 10, this is 5 times 10 to the negative 6th if it was playing ball with us. Okay. So, or 5 times 10 to the negative 44th power. All right, very small number. All right. So what I'm trying to get at is if you have something like this, if you have a bit pattern, that same bit pattern could be found in an int or a float or a char or whatever, and it needs to know how do I interpret these bits as a value. So if it was an integer, it would be the value. Anyone know what this is? I don't think I've told you what this is yet. What is 101010? The 32-bit set, the 8-bit set, the 2's bit set. So 32 plus 8 plus 2 is the magic number 42. Okay. I was worried about how often the number 42 came up in my life. And so when I turned 42, I was like, okay, well, nothing bad's happened. And then COVID started. So yeah. You're welcome. So if we were to see out Bob here, we get 42. Okay, do you guys understand what the type really means? Like when you say Bob is of type integer, we're telling it how to interpret the bits within it. That's really what the type means. Like early on, we're like, oh, it tells you what kind of values it can hold. But really, all variables can hold the same values because all variables hold 1s and 0s, right? They're all the same under the hood. In RAM just holds a whole bunch of 1s and 0s. I got 64 gigs of RAM on my system here. That is 64 billion 1s and 0s. All of them actually hold the same data. All of them hold binary. What the type of a variable means is how you interpret the bits within it. So what if I changed Bob to be a character? Let's add another 1 here. So it's 42 plus 64, which is 106. Let's see. Let's try this. What value is this? An integer. If this was an integer, what value would this be? The 64-bit set, the 1-bit set. This is 65. But it's not an integer anymore. It's a character. So what do you think this is going to print to the screen? You think it's going to print 65? The bit pattern is the same as 65 for an integer. But what do you think it's actually going to print to the screen? A? Let's find out. Yes. The letter A is 65. And if you're ever curious about that, you can always type man ASCII, and you can see right here that the letter A is 65. Lowercase a is 97. So if we were to do that, we lowercased it. And that's deliberate. There's a reason why the lowercase numbers are 32 above the uppercase. So that if you want to uppercase something, all you do is just set that bit to 0. If you want to lowercase something, you set that bit to 1. So it's actually faster than you might think to uppercaseify and lowercaseify things. But the point is that when we see out this value, it's interpreting 110001 as lowercase a. Are you guys with me on this? What the type means is how do we interpret the 1s and 0s inside of it? Because all variables hold 1s and 0s. Okay? Philosophically speaking, do you guys understand types a little bit better now? Like what a type actually is. And they have other properties as well, like what kind of operations can you do on it? Right? If you have a string, hello, can I say string plus equals 2? It is less murky now. Excellent. Can I add the number 2 to a string? For those of you that are Python people or JavaScript, probably like, yes, you can. Of course you can. Why couldn't you? You can do everything with a string in JavaScript. Is this valid C++ to add 2 to a string? You can add 2 to an integer. You can even add 2 to a character, because characters are technically integers, even though they don't look like it. Can you add 2 to a string? Survey says yes. What about multiplication? All right, it already gave it away. No, you can't multiply a string. Now, what does this addition mean? Like, this might make it a little bit more clear. What if I add the letter A to a string? What do you think that's going to do? Or let's make that exclamation mark. What do you think is going to happen if I add an exclamation mark to the end of a string? Now we got hello, exclamation mark, right? So when we added 2 to a string, it's adding ASCII code to whatever that is. It's a control character or something. So, but if we were to add, I don't know, 65 to a string, what do you think it's going to be now? Hello, A. It's Canadian. Right? So the strings have a plus equals operator defined on them. But do they have a minus equals? Can I minus equals things on a string? No. Can I divide equals? No. Can I times equals? No. Can I set it equal to 65? Unfortunately, yes. And this is actually, in my opinion, bad C++ design. This will compile. Will it run? Okay. So, I don't like this. I don't like this. Okay. So, so a type is actually 2 things. So the type is how are the bits interpreted. The other part of a type means what operations can be done on it. So for an integer, what operations can we do on an integer? What kinds of things are allowed? This is a softball question, guys. Come on. What kinds of things, what operations can be done on an integer? Addition, yes. This is not a trick question. Multiply. Plus equals, plus minus, multiply, divide, equal sign, comparison, exponentiation, right? There's basically anything you can think of, like, you can do with an integer, right? Even do something like this. Left shift it once. Wait, the double left arrow operator, isn't that the cout command? Nope, that's the left shift operator. And so what that does is it moves all the bits in the number left one. So the 1 becomes a 2, the 2 becomes a 4, the 4 becomes an 8, the 8 becomes a 16, the 30, right? So it doubles the number. So if you wish to amaze your friends at a party, you can multiply a number by 2 by left shifting all the bits in it by 1. Okay, maybe you have cooler friends than I do. But yeah, this is actually the same thing as writing 20 right here. Because I took all the bits and shifted them one to the left. And then we output it, we get 20. So all sorts of things you do with integers, okay? Strings, maybe not so much. Yeah. Maybe not so much with a string. So types limit the kind of operations you can do on something. So can you do modulus on a float, for example? Float f and g, cout f modulus g. Is this valid C++? Can you take a remainder when you're in floating point world? Not seeing an error. Not seeing an error. There's the error. Right there. You cannot do modulus with floating point numbers. So the types restrict. You guys understand this? Like, you can do modulus with an int. You cannot do it with a float. So the type is part of like this like restriction system, or it's called type safety almost. Like, there's some things that are allowed, there's some things that are disallowed, and C++ checks to see if it's allowed before you can run your code. Other languages like JavaScript are like, let's try it. Let's see what happens, And who knows what you get, like, it'll try and run, and you just get all sorts of horrible, miserable results as a result of it. Okay, so the next thing you need to know about a variable: the name, the type, the value. What is the value of Bob? What value is Bob here? Here. Yeah, let's set it back to A. Do you remember what? Do you remember what number A is? ASCII code A. You ever watched The Martian? Matt Damon uses an ASCII code table to send messages back to Earth. A is 65. That is correct. Okay. And now we're getting to the meat of the problem. There is a fourth thing of every variable that you've probably never seen before. And the thing you've never seen before is the address of the variable. Okay? And you've probably never seen it. And the reason for that is because it's considered scary to know where in RAM your variable is. I don't know why, but if you think about it logically, every variable you have has to have some place where, I don't know why I'm pointing at my coffee. The coffee's in the cup. This is its address. I don't know. That's a strained analogy. Every variable you have has some spot in RAM that holds the value, right? There's 32 bits in an integer. So somewhere in RAM, there's 32 bits set aside, and it's got the bit pattern for that integer you're holding there. Okay. So, or in this case, it's a char, so it's 1 byte. It's 8 bits. Okay. So I can print the address of Bob like like this. Okay. And this is going to give me the location in RAM where Bob lives. You want to see? Sounds like pointers? It is a pointer. Pointers and references and memory addresses are all the same thing. It just means you're talking about the whatever spot in RAM that variable is. You guys ready to see this? You want to see where in RAM Bob is? His home address. My home address is 1234 Main Street. Okay. It's exclamation mark. Wait, what? Let's make it an integer. A char star, by the way, is a string. And so it just reinterpreted that as a string and printed exclamation mark, which is hilarious. So another part of bad design in C++. Char stars are strings in C. There we go. So here's the address of Bob. Okay, 7FFC64-367A34. That spot and that spot alone holds Bob. Okay? And if I want to print the value at that memory address, I can do so by putting a star in front of it. This is exactly the same thing as scouting Bob, but 33, that's all right. Did I delete a 0 in there? I must have. 1, 2, 4, 8, 16, 32. Yeah, I must have deleted a 0. Okay. There we go. So Bob's value is 65. But what this code here says is give me the address of Bob, and then the star says print the value at the address of Bob. And essentially these two operators cancel out, and you just are printing Bob. Okay. Now, why do you care about the address of Bob? You usually don't. And that's why this thing, I left it as a question mark, is usually, yeah, you just don't care, right? Like if we have int Sydney here, let's go to 42. We print out the address of Bob, we print out the address of Sydney. And you'll see that they're actually next door neighbors. Look at that. So 7FF is very near the top of memory. 7FFFFFFFFF is very top of RAM. These guys are very near the top of RAM, but not quite. And you can see that Sydney here is 4 bytes away from Bob. Bob is 4 bytes long, so they're actually right next to each other in memory. Okay. And if you want to do some horrible C++, you can like take the address of Bob and add 4 bytes to it, and then write to it, and it's going to change the value of Sydney. We call that job security. You want to see that? It's horrible. Do you want to see that? This is what we call job security code. So, for example, if you're getting if you're in danger of being fired, you could write. I mean, you could just bear with me. You could write 65 here. That's fine, but that's not going to scare anybody, right? So instead, what you do? What do we have here? 1, 2, 3, 4, 5, 6, 7. 32-bit number. We need 25 zeros in front of this, so I'm going to type 25A0 escape. Boom, this is a lot more scary, right? And then, you just say, don't touch this, talk to Kearney first. There you go. Now they can never fire you, because nobody has any idea of what's happening with Bob. Like, oh my gosh, that looks terrifying. It's just 65, but with code like this, your boss is like, oh, we can't fire him. He's the only person who understands what's happening here, so. There's all sorts, like instead of 42, of course, you have 21 left shifted once, that's the same thing as 42, but, also like do not touch, or everything will break, you have been warned. Okay. And so you can just make your code, hideous and ugly, and then they can't fire you. It's great. It's fantastic code. So if we wanted to, let's see, how would we do this? Let's see. So Sydney's currently 42. So if we say address of Bob plus 1, because it should move 1 integer to the right since it's typed. The address of Bob plus 1 dereferenced equals 666. Okay. And then we'll output the value of Bob and Sydney and see what we get here. see if nobody can fire you now. There you go. So Sydney's value is now 666. I mean, you could have just written Sydney equals 666, but no. Nobody can touch you now. You are unfireable if you write code like this. I mean, of course, they might fire you for writing code like this. Like that's the flip side, right? Like this may cause you to get unemployed, but if you have your senior developer is looking at you like, what the hell are you? Why are you writing code like this? It's terrible. Who taught you? And then you just point them to this video, and you can see that I'm joking. I'm joking. I'm not being serious right now. Okay. We're having a little fun here. Okay, it's not serious. But it is kind of hilarious, honestly. Okay. So this is getting the address of Bob. It's adding 1 to it, and then we're getting the value there and setting it equal to 666. There you go. This is a very complicated way of setting Sydney to 666. Okay. All right. So do you guys understand the address? It's kind of like the analogy that I used in the previous class, which I kind of like, is have you guys ever been to like a self-storage unit? They have these like roll up security doors and like you got too much junk at your house, you just put it all in self-storage and then never visit it again. And then once you stop paying it, then you get to go on your family loot gets to appear on a TV show, and the people show up and auction off your collectible Coca-Cola mugs you got from a movie theater in the 90s. So let's talk about references or addresses. So addresses, sometimes called references, sometimes called pointers. There's technical differences, but they're all basically the same thing. Okay. So let's say we've got Bob here. Okay. And Bob, this is a little self-service, storage rack, And this is 114. This is Bob's. Okay. And next door to Bob's is 118. And this is Sydney's self-storage. And inside of here, Sydney has the value of 42. And inside of here, Bob has the value of 65. Fancy. Yep. You guys understand? And they're next door neighbors, right? So Sydney, inside of this memory address, I'm not going to repeat 7FFF, whatever. We're just going to say this is memory address 114, and Sydney's at memory address 118. They're 4 bytes away from each other because Bob is 4 bytes wide. Okay. So there's a couple different ways that you can actually change the value of Sydney, as we just saw. Like we could say Sydney equals 420, and then we would just change, like if you just wrote this code here, right? Sydney equals 420, then voila, we've changed the value of Sydney to 420. Or we could do something horrible like this. This here in English means go to the address of Bob, 114, and then go 1 to the right. Plus 1 doesn't mean 1 byte to the right. It means 1 integer to the right, and an integer is 4 bytes. So go 1 storage container to the right and set the value there to 666. And so what happens here is, like imagine you give somebody like directions in real life, like go to my storage unit. My storage unit is number 114, and then go 1 to the right and, open that one up and then change the value inside of it, right? And so that's how we changed the value of Sydney. We changed it by using the address rather than using the name. When you're working with variables, you can actually use the address or the name to change the things. Like here, we used the name, Sydney equals 420. Here we used its address. We got the address of Bob, we went 1 to the right, and then wrote into it there. And and this works in real life, right? Like if you hand somebody a sheet of paper and say go to storage unit 118 and take everything out of there, like that's not like right. That's not hard to understand. Here you go. It's what we do all the time, right? Here's, you order DoorDash, here's my address, You don't say deliver it to Bill, you say deliver it to 1234 Main Street, right? And then they go to your address and drop off the food. So you can work with variables either using their address or using their name. Both of these work for, reading and writing the values. Okay? That's kind of the big thing here. You guys understand? You can either read or write these variables, the values at those variables. You can either read or write them using the name or the address, or both interchangeably. Like on one line you do one, on another line you do the other. If you guys understand this, you'll be fine. Do you guys understand this? Like, go to this address and do something. Okay? I'm confused. Questions about this? Don't write code like this, by the way. Don't do that. Okay. So now we're going to see why this matters. So all of the we are like, 'cause this is stupid, right? Like, let's be honest. Nobody writes code like this, unless it's a joke, like I'm doing here. If we come up here, void function, call by reference. So we're going to learn the difference of call by value versus call by reference. And this is something a lot of C++ people struggle with because they don't understand the difference between them. So what we've done until now is called call by value. Okay. So over here, we've got a function, and this copies the value of, I don't know, what are we doing down here? F of 40. I don't know. This copies the value of 40 into a new variable named x. Does that make sense? So if I change the value of x here, this doesn't change the value down here. So if I have integer points is equal to 17, and I pass points to this function, even though I'm changing x here, this is a different variable than points. So when we do call by value, it copies it. It makes a copy of the variable. This guy here is a different variable from this guy here. All right. So if I come back to my analogy over here, let me get my face out of the way. When you call f of x, this pure function over here, right, and you pass the value of 17 into it, this is a new variable. Integer x is a new variable. And so if I draw it over here on my self-storage unit, this, at address 122, because remember they're all 4 bytes apart, it may or may not be adjacent, but it doesn't actually matter. The actual address actually doesn't matter as much as you'd think. And then we're passing in the value of 17 to it. All right, which I'll switch to the beautiful font there. And we're calling this variable x. You guys see that? So even though the original value of maybe we'll just use Bob. Let's do this. Okay. Then I don't need to make another. I don't need to make another entry on my graph here, right? So we're passing in 65, right? And then what happens is x over here is a brand new variable, and it's set to 65. You see that? So now we have two variables named 65 that hold the value of 65. This is called called by value. Call by value clones. So call by value, which is the regular way of passing a parameter, call by value clones the variable. You guys understand? It makes a brand new variable whose value is the same as the old value. And then if I change it, if I double this, right? If I set this to 130, which I believe we do over here, right? Right here, right there, we're doubling it. The clone changes values, but the original doesn't change, right? So back here in main, Bob does not change as the result of this. You guys understand this point? So with call by value, you pass the value to f. It makes a brand new variable with the same value, and then you can do with whatever you want with it. Doesn't matter. Then it vanishes. So when the function returns, when that line of code runs, then X vanishes. It's gone. It's deallocated. And now we're back in main, and we're back to just having Bob and Sydney again. Okay? So that is call by value. Call by value copies the value into a brand new variable. And this is great, except when it's not. Okay? So what if we had a function, I'm blurry again. What if we had a function like this, void search in string, and we're going to take a string stir and a character C, and we'll even make this bool, and we're going to make this even, heck, we're going to make this a pure function. Why not? Let's do this. Okay. And so what we want to do is see if the character C appears within the string S anywhere. Okay, let's see if we can get it to focus on me again. Who cares? Okay, so we can do something like this for, shoot, I've already used shit. Okay. So for every character C in string, if C double equals ch, return true, else return false. Okay, so here's a very simple function that will search through an entire string and return true if that character appears somewhere within it, and return false otherwise. So if we have down here, scout bool alpha search in string, let's say we pass in twas Brillig and the slithy toes did gyre and gimble and the wabe. All mimsy, how do you spell mimsy? All mimsy were the borogroves and the gnome wraths at brave. Anyone know what that's from? Probably misspelling it, but it's not real spelling anyway, so who cares? Close quote. Let's see if the letter Q appears anywhere within it. Anyone know where that's from? Jabberwock. Yeah, it's from the Jabberwock. Thing just refuses to focus. So weird. Yeah, it's a Jabberwock. Beware the Jabberwock, my son. The jaws that bite, the claws that catch. Beware the Juji bird, and shun the frumious Bandersnatch. He took his Vorpal sword in hand. That's where the word Vorpal comes from. If you've ever played D&D, it comes from the Jabberwock. He took his Vorpal sword in hand. Long time the maxim foe he sought. And rested he by the Tumtum tree, and stood a while, and thought. And as in uffish thought he stood, the Jabberwock, eyes aflame, came whiffling through the Tolgi wood, and burbled as it came. 1, 2, 1, 2, and through the Vorpal blade went snicker-snack. He left it dead, and with its head he went glumping back. Oh, hast thou slain the Jabberwock? Come to my arms, you beamish boy. Oh, frabjous day, Callooh, Calais, they chortled in their joy. 'Twas Brillig, and the slithy toes did gyre and gimble in the wave. All mimsy were the borogroves, and the gnome wraths how great. Thank you. No, I'm not reading it. I've memorized, dude. Cool. Okay, so there is a B inside of the string here, right? Capital B, right? And there's also kind of a lowercase b in there somewhere. Thank you. And so it's true. But if we search for Q, there is no Q inside of there. And it's false. Yep. Now, what's the problem with this? Well, the problem is we're copying this entire thing, right? So so this is maybe not that big a deal for modern CPU. But what if you had the entire Wikipedia inside of a string and you copied it? Is that efficient? Is that fast? What do you guys think? We're doing this. It's going to duplicate the entire Jabberwocky, right? It is very slow, indeed. and unnecessarily slow. Like sometimes you want to copy something, like, you know, because you want a copy of it. But here, instead of a number, copying a number is cheap. Like, who cares? It's fast. But here we have, you know, 'twas Brillig and the Slithy Toves did Gyre. Da, 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 da. And then when we call this function over here, it's still blurred. So, wow. No idea why this thing just refuses to focus. When we call this thing here, we're creating two new variables. We are creating stir and ch. Got stir over here, and we got ch over here. And stir is going to get a copy of this. So it's going to be 'twas Brillig and the Slithy Toves, the Gyre Gimlin, the Whale, Minister of the Borgroves, the Morass, okay. And then the ch is just, you know, q. So this is fine. Copying ch is fine, right? Nobody cares. It's, you know, copying a character is trivial. But copying, like, all of Hamlet, you know, well, that's going to take a while because you have to go character at a time and copy the whole thing, and there's no particular benefit for it. So here is the learning point for today. We want to pass it by reference. If you pass it by reference like that, what happens is search and string, and it's mad at us because it's not constant, okay? So in general, there are two ways that we pass things in C++. There's actually four, but there's two main ways. So call by value, you pass ints, floats, doubles, characters, basically all primitives pass by value by default. Okay? Call by reference, and usually call by const reference, which is what we have here. The const means you can't change it. Okay? It would be really weird if you're searching through a string and see if we can get this focused. Irking me. Probably more than it irks you. There we go. Call by const reference is the other default reference here. And this will be used for strings and vectors and other large things. These things you pass by const reference, which looks like this. So what does this mean? This means we're passing the string in, but we're not. We're not actually copying it. What we're doing when you pass in something by reference is, even though it looks exactly the same, do you see that? Like, I didn't change any of the code in here, right? All the code here is exactly the same. All of this code is the same. I didn't change anything. Call by value, call by reference, the code's exactly the same. But what happens underneath the hood is this. It is going to pass in 114 underneath the hood. So rather than passing in the entire play of Hamlet or passing in the entire Wikipedia, it passes in the address where it can be found. So starting at memory address 114 is, you know, the Jabberwocky by Lewis Carroll, right? And that's way faster. You guys see that? Like, all you have to do when you pass in, like, all the, not you, but all the compiler does when you do this is it's just passing in the memory address. That's it. 64 bits. Makes sense? Much faster, right? Like, if you have a gigabyte in your string, you pass a gigabyte by value, it has to copy a gigabyte of data before it can do anything. When you pass it by a const reference, it just says, hey, this string that you're wanting to read, it's here. Let's just add this memory address. And then underneath the hood, like, you don't have to worry about it. It's actually going to execute different code. Like, every time you read and write to the string, it's going to first say, oh, the string is over here, and it goes over here, and it reads it. Okay? And so every time you access string, it's going to have a layer of indirection in there where it's pointing at, this is pointing at this memory address here. And then it goes there, and then it messes with it. Any thoughts on that? Is this easy to understand or hard to understand? You will not see any difference in correctness between this and this. Exact same output. The only thing that's happening is under the hood, you are not copying the Jabberwocky. when you pass it over. Wow. Yeah, and range-based for loops work the same way, right? So this is call by value. This is making a copy of C every time. And so if you were to modify this, if you were to like set, I don't know, if you were to like set C equal to blank space or something, and I'll write your name, then this won't do anything. Why? Because we've made a copy of every character, and then we're clearing the copy and then throwing it away, right? Because this C here vanishes at the close bracket. So we're changing it and then discarding it. So who cares? It doesn't do anything. This line of code is completely non-functional from a practical standpoint. If, however, we passed it by reference, like that, then this would erase the string, okay? And that's why we pass in these things as const reference. Because if you pass in a string by reference, what happens is you can accidentally delete the string. Like if you're passing Hamlet to a function and hunting through it to find the first instance of Ophelia, then you could erase it by accident, which would surprise people. It's a find function. It's a search function. It shouldn't be erasing my string. You're like, oh, oops, my bad. So when you put const there, that const prevents you from changing it by accident, and that's good. The only time you leave the const off is deliberately if you're trying to change the string. So call by reference is used only when you are wanting to modify the variable. Is this pure? Absolutely not. Right? Because you're modifying something back in main. Right? This is not a pure function at all. And so if you wanted to do something like this, where you're saying stir equals hello, right? This is any string you pass in is going to be wiped, right? So if we have a string stir equals hello world, and I do search, it's not very well named now, search in string stir q. This function here, what is it? Why did you do that? Okay. So search in string here is going to erase string. So we're passing in hello world, and here it's going to erase it, right? And that's probably not what we expect. You know what I mean? Like if I call a function called search in string, I'm not expecting this to delete my string. So that's why we usually use const reference for everything. The only time we do something like this, where it's actually just call by reference, is if you're trying to edit it deliberately. And this is generally considered bad practice. It's not exactly, I do this. There are reasons to do this. For example, in your lab time, I will give you just one of the answers right now. I just dropped my tablet. Oh well. I broke my last one because these things have a little micro USB cable that are just super flimsy, and when you drop them, it just puts all the force right on the connector, and then snaps the connection. So I've got another tablet here that doesn't work anymore. So let me show you a place where call by reference would legitimately be used. We will call this uppercaseify. String by reference. Again, if you don't see a const there, by default, I put a const. Every time I pass a string, it's always const reference. That's the rule. Because you do not want to copy a gig of data. You just want to pass the memory address and be done with it. The only time you'll see me write call by reference is if I'm essentially telling you I am changing this string. And what this is going to do is this will uppercase all the letters in string. Okay? So for every character by reference in string, C is equal to 2 upper C. Okay. So if I put in hello world and I uppercaseify stir and C out stir, why does it keep jumping like that? It's so weird. It's like the language server is like lagging today. Okay. You guys see the code here? So we've got a string. It's got hello world, capital H, capital W. Everything else is lowercase. I then call uppercaseify on it. And so this is actually going to modify in place stir. It's not making a copy. If we were doing this with a pure function, then this is what I was saying. Like pure functions can have a performance cost. If we were doing a pure function, you would take in a string and you'd make a new string that was an uppercase version of the old string. And so if you passed in a gig of data, you would end up duplicating it and passing out a different gig of data, which isn't great. You know, it's not great. And so this would be a place where call by reference is the correct move. And an impure function is the correct move. It modifies the string in place. So all of the letters, this is saying for every letter in the string, set that letter to be the uppercase version of that letter. And so this is going to go from hello world to hello world shouting. Okay. Another way we could do this, some students were trying to do this in the earlier lab using a regular for loop, and that's fine. For integer I equals 0, I is less than stir.size, I plus plus. So this here is option 1, and this one is option 2. And so we could say s.at I, which is the ith character. The first time through the loop, it's going to be the 0th character, the first character. The next time through the loop, it's going to be .at1, .at2, .at3. So it's going to go through the entire string, starting at 0, going to less than size. So if there are 10 characters, it'll go from 0 to 9. And we're going to set it equal to the to-upper version of that character, s.at_i. So the first time through the loop, character 0 is going to be, not s, the first time through the loop, we're going to grab h. s.at0 is capital H. We then call toUpper. toUpper is a pure function. It takes in capital H. It returns capital H. Cool. And then we set it to capital H. Next time through the loop, I is 1. s.at1 is E. And so this is H is index 0. E is index 1. L and L are index 2 and 3. So as we go through the loop, we grab each character one at a time. We grab E, turn it into capital E, and set it to capital E. Next time through the loop, we grab L, set it to capital L, etc., etc. If we get anything that is not a letter, it just remains the same. The uppercase ampersand is a ampersand. Okay. These two functions do exactly the same thing. So, or these two loops do exactly the same thing. So what I want from you guys now is to do mocking SpongeBob correctly. So I want you to write a function called mocking SpongeBob. Lab time. Here we go. Where you randomly uppercase and lowercase each letter. And lab time number 2, make an add function that outputs the result into the first parameter. So it's going to look something like this. Void, is it pure? Probably not. Void functions are pretty much all impure. Integer by reference, named outVal, int x, int y. And I want you to, your code should set outVal equal to x plus y. Okay. And the way that we write this in code is we're going to say output parameter, unusual DM activity detected in ACM check. Yeah, we're getting a security warning. Interesting. Okay, output parameter, outVal, and input parameter x and y. So if you do something like this where you're writing to a parameter, usually parameters on a function are, you pass them to the function, it manipulates them and returns a result. Sometimes rather than returning a result, you write to a parameter using call by reference. This is generally considered bad practice. I don't want to say it's bad practice. There are definitely times when you want to do this. Like if you have to write 2 return values, well, you can't do that with return. Return returns 1 value. You can do things like make a struct and tie and things like that. But sometimes if you just want to return 2 values, you just have appval1 int appval2, also by reference, and then you're going to call it like this. I need function names. Apple, banana, and then add apple, banana, 10, 20. And so what I want you guys to do is to store the sum of 10 plus 20 into both apple and banana. So essentially you're returning two parameters, but instead of using return like you should most of the time, you're writing the results into two different variables. Yep. And that is your lab time. Begin now. You have 25 minutes, and I will show you the answers then. And welcome back. So here we've got, this looks like this was originally uppercaseify that turned into a mocking SpongeBob attempt. So what this is saying, okay, so first of all, when you pass a string that you're going to change, right, you want it to be called by reference. Secondly, this needs to be called by reference so that you can modify the characters in the string. Here, you're generating a random number from 1 to 10. If the character is greater than 1 to 10, which it always will be, because remember, capital A is 65, and that's the lowest character. So 65 is always going to be greater than X, right? That's always going to be true. So then you are going to set stir the string equal to the uppercase version of the character, which you can't do. What you want to do is say the character is equal to the uppercase version of the character. And stir.at_c, this is going to cause a out of bounds error here. This just should be C. And don't C out it, unless you're trying to debug it, okay? And yeah, I think what you're trying to say is like if, I don't know, if X is greater than 7 or something like that, then, you know, if you roll an 8, 9, or 10, 30% of the time, uppercase the letter, otherwise don't. And so this is a fixed version. If you're using the range-based for loop, you cannot use stir.at_c. That is bad, because this is going to go to what character in the string, whatever the ASCII value of the character is. So if you pass in, if the string starts with capital A, it's going to go to the 65th element of the string and crash, because there is no 65th element of your string probably. So don't mix and match those two options. When you are using the range-based for loop, you just work on the character C. C is the ASCII code of the first time through the first letter, second time through the second letter, third time through the third letter. If you're going to be using the regular old school for loop here, then you use stir.at_i, not C, I. I is the index into the string. So starting at index 0, going to index 1, going to index 2. Don't use the ASCII value as the index. Those are incommensurable values. Don't use those interchangeably. So you either do it like this, or you do it like this. Okay. All right, so let's take a look at some of the other options here. Uppercaseify for character. Oh yeah, that's the same one I just looked at. All right, SpongeBob, pass string by reference. That's good. For every character in the string, you're generating a random. What's going on with this? I don't know. Okay. You flip a coin. I see what you're trying to get at. Okay. All right. Yeah. Okay. I mean, I would just do that with like if rand modulus 2, right? Like that's the thing we were trying to go for. Else YYP shift R lower like that. Okay. So flip a coin. So rand generates a number from 0 to 2 billion. Modulus it by 2 to get the remainder, which will be either 0 or 1. If 1 is true, 0 is false. So if it's true, then it uppercases the string. If it's false, it lowercase-fies it. So we do that. then you'll see we get mocking SpongeBob hello world. Let's see what else we got here. So for every character in the string, you first lowercase it, then you flip a coin, and if the coin comes up heads, you uppercase it. You don't need that double equals 1, because remember, 1 is true. So if you just say if rand modules 2, fine. But this is fine too. There's nothing wrong with that. And then for the other lab time, we're outputting into these parameters here, right? So we're writing the results of x plus y into outval1, x plus y going to outval2. Perfect. It's a perfect implementation. Definitely not a pure function, but some people like coding that way. And then, let's see. Is that it? Only 3 people posted their code? Mua, Fernando, Gunnar Lamar, Jawin. Let's see some code from you guys. You guys had half an hour to work on it. Even if it's bad, this is how you get feedback by posting things. Just post it on the chat channel. I'm going to end the stream now, but I want to see all you guys post code. If you're just sitting here for half an hour without doing anything, just staring blankly at the screen, then you're that's not good. You need to be working, and if you don't know what to do, you need to ask for help. So sitting staring blankly at a screen waiting for class to end is no way to get through life. If you don't know what to do, then ask for help. Like, that's why I'm sitting here for half an hour. So Joanne, Garza, Olson, Mua, like let's see Fernando, Lamar. Like, I know some of you guys are at work or whatever. That's fine, but sorry, at work, it's fine. I understand. Yeah, but like, post what you got. I wanna see your work. This is all okay. That's good. It's good. Just post what you have. Like, I'm not like it's a mistake. Like, the only thing that bugs me is like if students like don't do anything, right, and not ask for help. Like, just post your buggy code. Let's see it all. Okay. So so you did call by value with extra steps, right? So this is a const reference, and then you're copying it. So it's fine. And then discarding it. So yeah, rather than doing const reference, you want to just do call by reference here, because this is a copy of it that goes away at the bottom of the function. So this won't actually change the value of input at all. It can't. It's a const, right? So for every character in result, if you flip a coin, you uppercase it. Otherwise, you lowercase it. Sure. And again, the double equals 0 isn't necessary. Right? Yeah, but good. All right, thanks everybody for coming out. I'm going to upload both these videos, and stay tuned for a very special homework assignment on, very good, we got one more here. Very special homework assignment on Friday, where you guys are going to get your pick of a homework assignment. So we're going to have 4 homeworks available for you, and you're going to get to choose which one speaks to you the most. And we're going to see how that goes. All right, so stay tuned for that on Friday. Peace out, everybody. Thanks.